welcome back to the channel. In today's video, we're going to be going over fluid statics and kind of like the governing equations for fluid statics. So, first things first is I'm going to draw this little cube, and it's going to represent like a fluid particle. Okay, this cube is kind of bad. And we'll give it a length of, or like a width, length, and everything's gonna be like, because it's a small particle, everything's gonna be infinitesimally small. So we're gonna have in terms of dx, dy, and dz. And so the two main forces we have acting are body forces, and surface forces. So since this is statics, our surface force is only going to be the normal force, or we're only going to have pressure, which is that surface force that acts that acts normal. Because we're not moving, we're not going to have like shearing stress. So let's take a look at body forces. So the only body force we really have to worry about is gravity. So if you want to write this, force body is equal to, since this is going to be small, it's going to be gravity, the acceleration due to gravity times this, right? And if we want to rewrite it in terms of density, let's say we have density is equal to, then we would have so this is in terms of density, what we're going to be used for body forces, and our surface force, that's when we're going to go into that right now, actually, which is pressure. We're going to go into pressure. So dV can also be rewritten as dx, dy, dz, because these are all this is kind of like the length, the width, and the height. So let's take a look at how we're going to do this pressure. So pressure, if we're going to have pressure as a scalar field, because we know pressure is not, we know pressure is a scalar field because pressure itself acts in the direction that's like normal. It's not it's not a vector field, right? It doesn't have its own components. And so now we have this pressure as a function of x, y, and z. So if we take the center position, we'll call it like O. And we want to find the pressure acting on these faces, right? Because pressure acts on faces, just like this. It acts opposite to the normal face and the normal vector. If you need to recall what the normal vector is, the normal vector is always perpendicular to our surface, our area. So let's come down here. Let's see, what can the pressure be at all these faces. So if we think of O, which is at x, y, z, coordinates are x, y, z, and we move in the y direction, if we move back, remember it's dy, we'll have our pressure minus, now we know that pressure is a function of x, y, and z, so we'll be using the partial derivatives. We're going to be having minus dp over dy, and because we're moving back and we're moving halfway through, because we start centered, we're going to have dy over 2. So this is what's representing our change in the y direction, and I'll show you exactly how, like more into detail about how I got this, right? And we'll have our dx, dz. Okay, so that's the y phase, and we have times the x and the z face. So let me actually elaborate more on this. So if you're not familiar with the Taylor series expansion, I'll go ahead and show you guys what that looks like. Basically what they have is the function f of x plus the df over dx derivative multiplied by that change. Okay, so we have our function, which is p, okay, minus, and df over dx, which is that derivative. Because this is a partial, we're gonna have that dp over dy, and we're gonna have this delta x term being this, or sorry, that change, which is dy over 2. Reason it's dy over dy over 2 again is because we're starting in that middle and we're moving back halfway. So now if we were moving forward, we would have p plus y over d2, and we can't forget about the other terms, dx and dz. So a quick side note that I think I forgot to mention in the video is that the reason we have that dx dz at the end is because the force from pressure. So we know pressure is force over area. So if we want to rewrite this in terms of the force, because we're dealing with forces, right? Surface forces, we'd have pressure multiplied by area. And because we have that infinitesimally, like, that small area, that cube, right? We have dx, dy, dz. We take a look at this plane real quick, y, x, and z, and we have our little cube thing. Oh god, I messed it up again. Okay, in this direction, like I was saying, pressure acts j, and if pressure is in the middle, and we use our Taylor series expansion, right? We had that, was it p partial p over partial y dy divided by 2. Okay, this is from the Taylor series expansion, by the way. So this surface right here is dx dz, that plane, that area, right? So this is pressure times the area, because this is an estimate of pressure. Taylor series is like estimating the function at a certain position, right? Doing that approximation, this is the area. I just wanted to make that clear so that you know this is and it's in the j direction. So just wanted to make that clear because I realized after I didn't go over that while editing the video. X and dz. And now because this one we moved backwards, we traverse backwards, our pressure is acting inwards, right? So this is the j direction. So this is going to be j, and this one's going to be the inverse, which is negative j. Okay, now we can also do these for the other function, the other directions, x and z. So I'll go ahead and do that. So if we take into account all the directions, we're gonna have these equations. That's kind of like the component form for our surface forces. Our surface force, which is just pressure. So now, if we want to find this, like the total, all we need to do is just add these together, and that's gonna be the sum of our surface forces. Remember that the total is equal to surface forces plus body forces yeah, I'm gonna go ahead and do that. Okay, so component form right here, and now this cancels out with that. Cancel, we got some nice cancellations here. And then this final form for this I, j, and k, well, not the final form, but a more simplified form would be negative. Oh, what the? Oh my god, I keep writing D2. That's how you know I'm tired. And I'm gonna take out the, how do I zoom out of this thing? There we go. I'm gonna take out the dx and the dz. I'm factoring it out of both of them. Dx, dz, and you can factor out the negative partial p over partial y, and dy over 2 plus dy over 2, that's just going to be equal to dy. So you should really be left with over dy. And this is in our j direction. And dx, dy, dz. Now if I do the same process for all of them, you'll be left with surface force is equal to negative dp. I kind of did this, I kind of wrote this differently than your standard notation. It should be I, j, and then k, but I'm kind of tired, and I hope you get the point. I, j, k, and here we're gonna have dx, dy, dz. This right here is a gradient, a negative gradient, and so negative del p. And this dx, dy, dz, if you remember earlier, I said this can be rewritten as dv. Okay. And now, if we want the sum of our forces, you remember that the sum was body forces plus normal forces, body forces plus surface forces. So this is surface force right here. Now we need to add that body force we found earlier, which was, I'm going to put this in row. I hope I didn't, I definitely butchered this. Gravity, this is supposed to be density, by the way. Density dv. So density dm over dv, dv, and m times g. So negative del p, del v. So this is going to be our mass times acceleration, right? So that's our statics equation right there. And well, because we know that that gravity only acts in the negative k direction, or depending on your axis, right? If we assume z is gonna be up, if we assume z is up and down, then we can say it acts in the negative z direction. So now we know that our fluid is static. Gravity is the only body force, and the z-axis it can be up and down, right? So now we have that. negative p dv plus p dv. So now if we have a static fluid, we can assume the acceleration to be 0, right? 0. And if we have, and we can take dv out of all of these. We can factor it out of both of them, and we can just divide them both. We can divide both sides by dv, and we'll just be left with plus pg, and that's pretty much the derivation of the fluid static equation, which is a pretty important equation. And that's the basic equation of fluid statics. That's kind of what this long video is just leading to. I hope you guys understood and enjoyed. Thank you for watching.